Hey everybody, welcome back to the channel. Today we are going to be deep diving into Cassandra, and this is specifically going to be through the lens of a system design interview. And so I'm going to give you the minimum amount of information you need in order to present this information in an interview, but enough depth such that if your interviewer probes, you can justify your decisions accordingly. So we're going to try to walk that fine line. Now, at a high level, before we get started, Cassandra is a distributed NoSQL database, and it's designed for handling massive amounts of data across many different servers without any given single point of failure. It's their high-level summary. Importantly, it was created by Facebook in 2007 by Avinash Lakshman. There's your guy right there. I'll paste him in. And why is he important? Well, he's important because he was also the co-creator of Amazon's Dynamo. And so when designing Cassandra, they took a ton of inspiration from both Dynamo and Google's BigQuery. And so if you're familiar with either of those technologies, then learning Cassandra here today is going to be a lot more straightforward because there's tons of overlap. We also have a video breakdown of DynamoDB. I'll put it in the description. I'll try to put it in one of the corners if I can figure out how to do that. And so feel free to give that video or that written breakdown a read as well. Now, Cassandra was created specifically to solve the Facebook inbox messaging system. And so they needed a database that could handle massive amounts of write throughput for millions of users, sending billions of messages in total every single day. And it needed to be able to scale horizontally, right, without manually sharding. It needed to be able to provide tons of availability with zero downtime. And it needed to deliver these super low latencies, reads and writes globally. And so that was the motivation. Now, in contrast to relational databases, which I'm going to assume throughout this video most of you have some basic familiarity with, Cassandra was designed to give up on flexibility in querying. So there aren't things like joins or strong consistency. But in exchange, we get three main things that every massive system needs. You can see them at the bottom of your screen. Highly scalable, highly available, and this fault tolerance. And so as we go through this video, we're going to talk about exactly how Cassandra achieves each of those things. And at the end, I'll tell you exactly how you should decide whether or not it makes sense to use Cassandra in your system design interview or not. So without further ado, let's get after it. Now that we know why Cassandra exists, let's talk a little bit about how it actually organizes data. And so the Cassandra data model looks a little different from relational databases, but there are still plenty of similarities that you can anchor to. Starting with the very top, we have what's called a key space. Now you can think of a key space just like a database in Postgres or MySQL. It's simply a logical container that holds your tables and defines some global settings. These are things like how data should be replicated across the cluster or how many copies of that data should be maintained. Now within each key space, you have what are called tables. And a table defines the schema. This would be the columns, the data types that can be stored. But importantly, unlike relational databases, Cassandra tables are actually flexible, meaning they don't require that every single row has the exact same set of columns. And that's, as I said, really important. I'll get more into that in just a moment. But within tables, you have rows. Each row represents a single record in the table, and it's identified by something called a primary key. We'll come back to how exactly these keys work in just a moment, but just know that rows can hold large sets of data and they're grouped together for efficient access. And then within each row, you have columns. This is the actual pieces of data. And so columns have a name, a type, and a value. Like in this case, the name is name, the type is string, and the value is Evan. And as I mentioned before, what makes Cassandra interesting is that it's a wide column store. If you've ever heard that terminology, wide column store, it just means that you can have completely different sets of columns within different rows of the same table. And so in this case, we have user 101 who has just 3 columns, name, email, and age, spelled incorrectly, I see. And then we have a second user here who actually has an additional column, an address. And this is fine. Whereas in a SQL database, you would need to define this rigid schema, and everybody would need to have an address. Even if that address was null, they would need to have a column for address. That's not the case here. We started off by talking about how Cassandra was built with 3 particular things in mind: scalability, availability, and fault tolerance. So let's talk about how it achieves each of these 3, starting with scalability. When you're dealing with millions, in some cases even billions of rows, then a single machine, a single server, can't possibly handle all of that data. And so in order to scale, Cassandra distributes that data across many nodes in the cluster so that each node stores just a fraction of the total data set, right? So in this case, maybe a fourth of the data ends up on node 1, a fourth of the data ends up on node 2, and so on. This horizontal scaling approach, I'm sure that's a terminology you all are familiar with, this isn't unique to Cassandra. It's how all distributed databases work, of course. But once you distribute your data in this way, once you split the data across multiple nodes, then you have a critical question that needs to be answered. Which node should store this particular piece of data? And this is where that partition key comes in. So when you're defining a table in Cassandra, let me scroll down here to it. When you're defining a table in Cassandra, you specify what's called a primary key. And that primary key is made up of two parts, a partition key and optionally a clustering key. Now, if you know anything about Dynamo or you watched our Dynamo video, then this is all very familiar to you. Dynamo is the same. It's partition key, and then we just call the clustering key a sort key instead. But the partition key importantly determines where data lives. So all rows with the same partition key are grouped together and end up on the same node, okay? The clustering key, on the other hand, determines how data is ordered inside of that partition. So to summary, partition key decides where the data actually lives in the cluster, and the clustering key decides how it's organized once it's there. So this makes the most sense when we have an example here. You'll see this statement here in order to create a new table for user messages in Cassandra. We define our primary key, which is made up of the partition key and the clustering key. In our case, we've chosen our partition key, importantly, to be the user ID. This means that all users, or all messages, from a given user are going to show up on the same node. This is important because if your query pattern was to say fetch all messages from a given user, then now you'd only have to hit a single node as opposed to having to query a bunch of different nodes and then merging or combining that data together at the end. And so if we scroll down and we look at this example, if we've partition key is user ID, then all the users with the ID 0 to 10,000, I made up random numbers here, just know it would be some fixed range, are going to show up on node 1, 10K to 20K on node 2, and so on. Now we have a way to decide what to partition by, but how does it actually map those partitions to the specific nodes? Now the simplest approach would be to use a hash plus a modulo. And so you can take the user ID, in our case user ID was the partition key, right? So take whatever value you're partitioning by, hash it, and then mod it by the number of nodes you have in your system. This is going to return a number of either 0, 1, or 2, so that you can know which one of these nodes it should live on. Right? So concrete example, if our user ID was 1, 2, 3, 4, and we hashed that, and we got some value like this is a made up value, of course, but maybe you would use a hash function like MD5. And then if we took the modulo of that, modded it by 3, then we end up with 2. And so we know that this goes on node 2. This partition should go on node 2. This works, but it falls apart at scale, of course. And the reason for that is pretty straightforward and shown via this diagram here. If you end up adding or removing a node, then the number of nodes changes, which means that nearly every key gets remapped to a new node. And so in a larger cluster, this would mean that you're shuffling terabytes of data around every single time you need to scale up and down. And so you can look at some of these simple examples. If all of a sudden we are now modding by 4 instead of 3 because we added a new node to the system, then everything that was previously on 2 probably shows up somewhere else now, right? And so as a result, we got to move all the data around. And this is a lot of work. And so to solve this, Cassandra uses what's called consistent hashing. And if you've been watching any of our content, if you know anything about distributed systems, you probably knew this was coming, right? But instead of using a modulo, consistent hashing is actually a really simple concept. It just arranges all of the possible hash values in a ring. Of course, this is just a virtual ring, right? But each node owns one or more ranges of that ring. And so when a key is hashed, in this case, we can hash whatever our user ID was. Maybe we get the value 16. Then we find that value on our virtual ring, and we walk clockwise until we find the first node, and that's where that data should live. And so by using consistent hashing, this design keeps data evenly distributed, and it minimizes movement when a node joins or leaves. And so if database 2 ended up leaving now, then everything between 0 and in our case 25 here is going to end up on database 3, but database 4 and database 1 didn't change at all, right? This is how we achieve that horizontal scaling. We can add and remove nodes without disrupting the cluster or redistributing everything. Now, importantly, this is a very high-level overview of consistent hashing. Consistent hashing has what's called virtual nodes, which make this redistribution more even. If you want to know more about consistent hashing, we have a quick video on it. I'll link it in the description so you can go check that out as well. Partitioning with consistent hashing explains how Cassandra is able to scale by determining where the data actually lives. But how do we ensure that we're always available and fault tolerant? The first thing that we need to consider is replication. Every single piece of data needs to be written to multiple nodes. And this is controlled by something called the replication factor in Cassandra, where that replication factor is a setting that is set at the key space level. So for example, if your replication factor was set to 3, then Cassandra keeps 3 copies of each partition on different nodes across the cluster. And so maybe the original data hashes to node 2, but we're also going to write it to node 3 and node 4 just to make sure that we have replicas or backups in case anything happens. These replicas they're placed strategically on different parts of the hash ring, oftentimes even across different racks and across different data centers. So there's a configuration, which I can't remember off the top of my head, but it's in the linked written article, which actually allows you to have your replication factor explicitly specify that replicas need to be on different racks or different data centers if you are in a global setup. This way, of course, if one node goes down, then the others can immediately just start serving those reads and writes. And if we lose data, or if we lose a node and it comes back up, then it can just learn from the nodes that stayed online how it should kind of catch up and repair its data so that it fits back into the cluster and starts operating again effectively. Unlike with many other databases, with Cassandra there isn't a single leader or primary node, and this is pretty interesting. Every single replica is equal, and any node can accept any given request. But if there's no single leader, how do all nodes end up coordinating? That's usually the role of the leader in the system. Like, how do you know who owns what, who's alive, who's dead? When things are added to the cluster, how do we know something was added? When something's removed, how do we know? Well, Cassandra handles all of this through something called the gossip protocol. And so every node in the cluster is equal. Like I said, there's no master, there's no central coordinator. And each node randomly talks to a few other nodes every other second, exchanging small bits of information. And so this is small bits of information like which nodes are up, which nodes are down, what data ranges they own, what schemas they should be using, etc. And so every few seconds, they ping these messages to each other. And if you ping it to just a couple nodes in the network, and then that node pings it to a couple other nodes in the network, then eventually all nodes in the network agree on some consistent state, right? Over time, that information spreads just like a gossip in real life, and then everybody has that updated, consistent view of the cluster. So this peer-to-peer design means that it's fully self-managing, and you can add and remove nodes, and the gossip will just automatically update the cluster state. Obviously, this is a sufficient simplification, but certainly for an interview's purpose, this is more than enough information. But this is how we avoid things like Zookeeper or etcd, which are used in many other popular distributed systems in order to be that central source of truth. But the benefit is that there's now no single point of failure for cluster coordination. So if you've ever dealt with, for example, a Zookeeper outage, which would bring down your entire system, then you know just how valuable it is to not have that single point of failure anymore. Now that we've introduced replication, and we've also introduced that gossip protocol for nodes to be able to communicate in this distributed network, something really interesting comes up. And that's that we've created multiple copies of the same data, which means that those copies could temporarily disagree with each other. So imagine that you have a replication factor of 3, you have 3 different nodes, you then write an update to your username. My username changes from Evan to Evan123. Well, if that write lands on one node and then gets propagated to 2 of the replicas, then there is a moment in time there where somebody could read from one of the replicas and still read Evan, as opposed to Evan123. And the question that always comes up in a system design interview is that okay, right? This is the topic of CAP theorem. So CAP theorem, as a reminder, says that in a distributed system, whenever a network partition occurs, right? A network partition here, of course, just means when some nodes can't talk to each other over the network, then you have to choose between 2 guarantees. Guarantee 1 would be consistency. This means that every single read returns the latest data, which was not the case in the example I just gave. Guarantee 2 would be availability, which would be that the system keeps accepting reads and writes, right? This is the option that we chose in that example. And so you have to choose one of these, either strong consistency or high availability. There is no both answer necessarily. And so Cassandra, of course, was designed to stay online no matter what. We talked about how the core of Cassandra is scalability, high availability, and fault tolerance. So it, of course, prioritizes availability and partition tolerance. If a few replicas are unreachable, it still accepts writes and synchronizes them later. That's why Cassandra is described as an AP system, availability and partition tolerance. But here's the cool part. And if you are in a system design interview and you kind of bring up this nuance, it's the sort of things that interviewers sometimes love to hear. And that's that Cassandra doesn't actually force you to pick one side, consistency or availability, forever. It lets you tune it actually per query. This is with tunable consistency, right? And so every single read and write that you issue to Cassandra, you can specify a consistency level. This is how many replicas must respond before the operation is considered successful. And you have 3 different settings here. The first is option 1. This is the one that aligns with high availability. And this is, we wait for just one replica to respond. And so if our partition is replicated on 3 different nodes, then we only need one of those to respond when we write a write. One of them can take it, tell us that it got it, and then we're good to go. And so this is of course the fastest, but it has weak consistency because this is the example that we opened with. You could still read stale data from one of those nodes that hasn't yet accepted that write. The second is quorum. This is the middle ground and oftentimes actually the most popular. And this is that it's just going to wait for a majority of the replicas. And so if you had 5 replicas in your system, a replication factor of 5, the majority would be 3. And so if you issue a write, it's going to wait until 3 of those nodes have responded saying, hey, I got the write down. And at that point, it'll respond to the user saying, write confirmed, right? And then the last one is all. This is where we wait for every single replica. And so this is for strong consistency. So in the case where we need that consistency, we want to make Cassandra a CP system, consistent and partition tolerant. Then we would use the setting all. We're going to wait for all replicas to confirm that they got the write. So with 1, you maximize speed and availability, but you risk reading outdated data. With all, you get strong consistency, but if any replica has an issue, like a network problem, a hardware failure, whatever it may be, then your request can't complete. And so most production systems end up using quorum, which is that sweet spot or that middle ground. Before I move on and I tell you what happens on each write and read request respectively, let's just check in and recap what we've discussed so far. We started with the data model, and then we learned that partitioning and consistent hashing is what allows Cassandra to scale. That replication gives it gives it availability and fault tolerance. That gossip and the leaderless design keep the cluster decentralized and self-healing. And then a tunable consistency lets you control how it balances correctness and uptime per each request. Really quick, before we continue, let me tell you a little bit about the most popular feature on HelloInterview.com, Guided Practice. It's an interactive tool that lets you practice system design interviews step by step using that Hello Interview delivery framework. You're going to walk through everything from the non-functional requirements to the core entities, API routes, all the way through to your high-level design and deep dives, drawing on the whiteboard and narrating your response, all while getting real-time feedback on what you're doing well and where you can improve by a model that Stefan and I have spent hundreds of hours tuning. We've expanded the library to 25 of the most common system design interview questions now, and we're constantly adding more. So candidates absolutely love this feature. I think you will too. Check it out at hellointerview.com. Link will be in the description. Okay, let's talk about the write path and the read path respectively. So what exactly happens when a client wants to write data or read data from Cassandra? Starting with writes, when a client wants to send data to Cassandra to write to the database, it contacts first any node in the cluster. This is actually really interesting. This is different than most databases where they have that central coordinator, right? Remember, we don't have that in Cassandra. So you contact any node in the cluster and that node becomes the coordinator for that particular request. And so that coordinator figures out which nodes own that particular partition key and it forwards the write requests to those replicas in parallel. So of course it has all of its internal memory based on the gossip messages that it's been receiving to know the full landscape of the cluster. So when the request comes in, it can send it to the write replicas to be able to service that request. And that's where this diagram enters. This diagram here on the right is a single clustered, or a single Cassandra node, okay? And so when that write comes in, we end up writing that data in parallel to 2 different places. We write it to 1, the commit log. This is just a write-ahead log. The write is first appended immediately to disk. Note that this is on disk. This is to guarantee that durability. If things were to shut down, we were to lose the node, we had to bring it back online, then it's important that the very first thing that we did is we persisted that write to disk, right? At about the same time, we're also going to write it into memory, into what is called the mem table. And so the mem table, you can think of it just like a sorted map of recently written rows. It keeps everything in order by the partition key and the clustering key, and it's fully in memory. It's in RAM. Okay, so this guy's nice and quick and fast. So that makes that write easy and fast. And then periodically, and this is asynchronous, right? So once it's written to the mem table and to the commit log, then we return back to the client saying, acknowledged, we've received that write. But then asynchronously, as the mem table fills up, it's flushed to disk into an immutable file that we call the SS table. This is sorted string table. And so SS tables are append only. They're never updated in place. And so instead, new writes create new SS tables, and the old ones are merged later through a process called compaction. And so I'm not going to go into a bunch of detail here, but it is a little bit interesting, though not relevant for a system design interview probably. But in a SQL database, you actually change the row. You change the particular data. If you want to update your name, then you find that row on disk and you update name to Evan123 from Evan. In the case of Cassandra, you never make those updates. You just flush this new mem table so you have new data. You have a new row that says Evan's name is now Evan123. And that means that every once in a while, what ends up happening is this compaction process, which goes through and compacts all of those old rows to say definitively Evans is 123 now. So you don't have to go read all of the previous updates in order to know the current state. I'm just going to tell you the current state because I've compacted all of those updates to make reads faster. So hopefully that makes more sense. I don't want to go, like I said, into too much detail there. But then finally, when enough replicas have acknowledged the write, again, based on that chosen consistency level, which we discussed a moment ago, then the coordinator can reply to the client and say, we've accepted this write. Everything is good to go at this point. But this is what makes, importantly, Cassandra's writes so fast. They're sequential disk appends and an in-memory insert. There's no random I/O. There's no finding the right place in a table. There's no locks. There's no coordination overhead. All of these things that exist in SQL tables don't happen here. We simply write to memory super fast, and we append to the end of a log on disk, an append-only log. Now, reads are just a tiny bit more involved. It starts off the same. The client again contacts any node, which is going to act as the coordinator. That node then knows which replicas hold the partition and queries them again in parallel based on the requested consistency level. But then each replica, and again, this is where we jump into this diagram here, right? So then each diagram checks two places. It first has to check the mem table in case it hasn't yet been flushed to disk. So it's going to check there first for any unflushed writes. Then it's going to check the SS table on disk. And so if it were to just check the SS table on disk, it would have to scan through every single row and try to find the thing that it's looking for. And this, of course, would be incredibly slow. This is the consequence of the fact that we have this append-only log in order to make writes fast. Well, on the other side, it makes reads slower. And so Cassandra has some fancy things that I'm not going to go into too much detail on, but it has some additional files in here, one of which is a Bloom filter, and as well as some indexes that allow you to skip files that don't contain the partition that you're after. And so some Bloom filters, some indexes, makes this read a little bit quicker so that we don't have to scan every single row. A bit more in that in the written guide, which is linked below, but that's how this ends up working. So you look first in the mem table, then in the SS table, then you respond back to the coordinator, and the coordinator takes the results of all of the replicas and merges them together, and it picks the newest value using the timestamp of the write. So whichever one is the newest, that's the one I'm going to send back to the user. But if the replicas disagree, then the coordinator needs to perform a read repair in the background to synchronize them. So there's these rare cases where maybe they were written at the same time, but they have different values. And then we need to figure out what the heck happened. But in short, it's this combination of this in-memory caching, this immutable disk file, these timestamp-based reconciliations. These are the things that give Cassandra these beautiful properties of really fast writes, that eventual consistency and high availability. And it's what makes Cassandra so great for these really high write throughput scenarios. All right, now before we wrap up, I want to talk a little bit about data modeling in Cassandra because of just how important it is to a system design interview. And that's that when you're designing systems that are going to end up using Cassandra, you need to model your data in a way that's going to take advantage of the architecture that we've been discussing throughout the video. Now, if you're coming from a relational database world, then this is going to feel a little bit backwards to you at first. So let me try to explain. With relational databases, you normalize your data, like you see on the left here. And so you store each entity once, usually in its own table, and then we use foreign keys in order to create relationships, and we can use joins to query across different tables, right? And so the relational data modeling is what we refer to as entity-driven, meaning you think first about entities and their relationships, posts and users. So in this example, we of course have the post table here, we have the user table, and if you wanted to query for all posts and their users, then you would query the post table, join it on user ID based on the foreign key here in the post table to the user ID. But this ensures that even if we have a post with the same user twice, they both still reference the same row in another table, right? That's the normalization. But in Cassandra, we don't have foreign keys, remember? And we don't have joins, and we don't even support queries across multiple tables. And so normalization actually works against you. Instead, data modeling in Cassandra is what we call query-driven. Maybe I should even write these down. So query-driven for Cassandra, and then this was entity-driven, right? And so it's query-driven. So you start by asking, what queries does this application actually need in order to run? And then you design your table specifically to answer those queries efficiently. So map your query directly to your table. And this means that you'll often have to denormalize your data, which leads to data duplication in order to make sure that each of those different queries are as optimized as they could be. And yes, this creates redundancy. That is the trade-off. And that's a trade-off maybe worth discussing in your interview as well. But in Cassandra, the argument would be storage is cheap, duplication is fine, but slow queries will end up killing you, so you can't do that. And so in this case, you see that we have a single post table, but now we've denormalized and we've put the user data in this same table. So that if I want to query in order to get all posts and their users, it's a single query to this table. It's fast and it's efficient. But you can see that we've stored, I guess this is actually not the, I don't know why that was Jane. There you go, now it's John. We've stored John twice here. We have his information twice here, and that's the data redundancy. So system design interview, if you're saying you're going to use Cassandra, but then you design normalized tables like you would in Postgres, it can be a bit of a red flag to your interviewer. It shows that you don't actually understand how Cassandra works. And so be careful, be sure that you demonstrate that you're thinking about the access patterns in this query-driven design. Let's answer the question that I know is most important to you guys, and that's when should you actually consider using Cassandra in your system design interview? Well, I've broken it down here to try to be as simple as possible, and that's that you're going to want to consider using Cassandra when you have really high write throughput. And we're going to describe really high write throughput as something over 100,000 writes per second. Now, this means that you're going to have far more writes than you're going to have reads, and it makes it a good candidate. And importantly, you should have predictable, limited query patterns. So there's a handful of common queries that you're going to run, which are predictable, and you know it's just going to be those handful of queries. Things like get all posts for a user. Right? That's going to be your main use case, potentially. I think Cassandra is a great fit. These are things like activity feeds, time series data, messaging systems, maybe event logging use cases where the writes are dominated and you know exactly where you're going to end up querying for the data. You can just denormalize across a few tables, and each one is going to be optimized for that specific pattern. Then Cassandra will scale beautifully and everything will work great. Importantly, there are places where you don't want to use Cassandra, where it wouldn't make sense to recommend Cassandra. And that should be any place, of course, where you need flexible querying, things like ad hoc analytics, complex aggregations, if you have joins across tables. Cassandra just doesn't support these things, and so it's not the right fit. And then critically, even though Cassandra has some simple support for lightweight transactions, these are transactions always within the same partition, it doesn't support any cross-table consistency, and certainly not cross-partition consistency. And so it doesn't have transactions that you're used to in an ACID database that can span these multiple tables. And if you need to write to 3 denormalized tables and one write fails, then you're left with inconsistent data across those tables. And so if you need strong consistency, if this is a financial app or a ticketing app or things like this, Cassandra probably doesn't make sense for that use case. Great. So we covered a lot in a short period of time. Hopefully you guys found it valuable. Just to conclude, I want to summarize what we discussed. And that's this simple. Remember that Cassandra is scalable, highly available, and fault tolerant. It's great for high write throughput apps with a few simple query patterns. And when you're using it, remember to consider your partition key. This is where the data lives. Your clustering key. This is how it's sorted on each partition. And then denormalization. What data needs to be duplicated in order to support all of your simple query patterns. With that, please leave a comment. Let me know if you have any questions. Let me know if I got anything wrong. Like, subscribe, all of those good things. We're going to continue to try to post one video roughly every 2 weeks. I'll have my LinkedIn down in the description. feel free to follow, shoot me a message. Always love to connect with you guys offline as well. And most importantly, best of luck with your upcoming interviews.